Okay, so just to briefly revise the content of what we did previously. So we discussed about rotating balancing, so both static and dynamic. We discuss how to balance a single out of balance mass, which you can see in this figure here. And then we also discuss ways how to balance if you have multiple out of balance masses.
Sir, I think you're on mute.
Can you hear me okay now?
Loud and clear.
Okay, so I don't know what happened. Okay, so this is the case when we have multiple out of balance masses. So we discussed these three cases, and then we solved one numerical example using the analytical method, the graphical method. So today we will discuss the analytical method, which is similar to this, but using analytical procedure. And you can use either graphical method or analytical method. Uh, Using both, you will get the same result. So we discuss about the static balancing. So I'm not going into the detail of these. So this is we discussed this knife edge experiment, and then we discussed the balancing of static cases. So when we have these different out of balance masses. Uh, so in case of static balancing, we just take care about the gravitational forces. And then in dynamic balancing, we then need to take care of the forces, which is what we call is centrifugal forces. So which is mr omega square, which you can see here. Uh, okay, and then so this was our final case, which is the most important one. And so in this case, for example, as you can see that you have multiple out of balance masses, so M1, M2, and M3, which is also given here in the in. Okay, so maybe if you people can just mute your mic, so it will be helpful. Okay, so in this case, as you can see that we then solve this case, and in this case, as you can see that we have because it's a very complex case, so we will have to need to make sure that the uh, summation of all the moments about AA is equal to 0 if you want to calculate the out of balance mass at location B, and then we want to calculate the out of balance mass at location A. So then you can either take the moments about B, or you can take the forces. Okay, so again, if you remember last time, we discussed about how to calculate the direction of the moments. So in this case, so I think if you will use the university email address, so then I don't need to give you permissions. Okay, so in this case, as you can see that we have this, we discussed this last time, that how you will calculate the moments, the direction of the moments here. So because as you can see that last time when we were solving that example, which was this example here. So we saw this example using the graphical method. So in this case, when we were calculating the moments, so we were taking the moments from D, and then yes, I'm not sure what is happening to the microphone. Hopefully it's okay now. Okay, sorry about this. I'm not sure what is happening. So, but if the microphone is not working, so please say it, because when I share my screen, so then I cannot see the things in the background. So what I was discussing is that when we were solving this problem, then the issue was that when we calculate the direction of the moment, as you can see here, so because in this case the force was positive, but we take the moment is negative, and we said that because it's on the one side, and if we take the force B, so it's on the other side. So that's why we take the force B, the moment for force B is positive, and the moment for force A is negative. Uh, so this can be explained using this slide here, which I also upload to the canvas. You can also look at there. So how it explains the moments is that how you will calculate the direction of the moment. So in this case, for example, if you have these three forces, which is M1, M2, M3, and now let's, for example, you want to calculate the moments. So if these are the moments in our case, so this is M1, M2, and M3. So we want to take moments from B. So B is this point here. So B is this point here. So you want to take the moments of this F1, F2, and F3 from this B. So you need to know that the moment is actually a vector, and it's a cross product of two vectors. So one is D and one is F. So D is the distance, and F is then the force. So if you take the cross product of these two vectors, so D and F, it should give you the the moment. So this means that if you take the cross product of two vectors, then the resultant is also a vector. So this means that moment is a vector, and it should have a direction also. So how you will calculate the direction? So it's again the same idea, that in your mathematics, when you do the cross product, so then the uh, direction of the cross product is, again, you use the right hand rule. So the way it works, for example, if you want to take the moments from B, so what you will do, you will just as you can see in this case here, in the right hand rule, so you can use the right hand rule. You just put your fingers in the direction of this D. So D in this case is now from B in this direction toward A. So then you can see that this is our D, and F is here. So in this case, what you will do, you will just curl your fingers from D to F. So if you just curl your finger from D to F, then the thumb will point in the direction of the moment. So that's why, if you can see, the direction of the moment is actually perpendicular to the M1. So because force is in this direction, then M1 will be perpendicular, because this is what we calculate by using the right hand rule. And similarly, if you want to calculate the moment for F2, so then it will be again perpendicular to M2, so which is going to be in this direction. And again, for M3, it will be in this direction, which is perpendicular to the M3. So what we do here, then we just rotate these three vectors, so M1, M2, and M3, in the clockwise direction here. So then it will just be aligned with M1, M2, and M3. So as you can see that in this case, in this specific case, uh, the actual moments are at right angle to the forces. But because this whole system is rotating, so if you take M1, M2, and M3 along the masses M1 and the mass M2 and mass M3 is given here. So it doesn't make any difference, because the relative position is important, not the absolute position. So this means that the actual moments are at right angle to these masses, but because then we can move these and we can make them align with the forces. So this is how you calculate the direction of the moments. And in this case, we are taking the moments from B. So this means that all the forces are in one direction. But assume that if you have a force on the other direction of the B, so for example, if you assume the similar force as F1 on the other side, so then if you put your fingers up the right hand side of the right hand in that direction, and then you curl your fingers, then it will be in the downward direction, not in the upward direction. So this is the main difference, that if it is on one side or on the other side. So hope this makes sense. So if there is any question in this, so think about it, and then let me know. And now I think we can move to the other question. So it will be better if I share my other screen. Okay, so as you can see that we are here trying to solve this problem here. Uh, so we solved the same problem using the graphical method. Now we will solve the same problem using analytical method here. So if there is any question, so please ask. You don't need to wait for the end. So just ask either in the chat or maybe you can ask in the just raise your hand. So again, we have this same system here. So as you can see that you have a shaft here located in two bearings D and E and carries three pulleys. So A, B, and C. So we have these three pulleys at location A, location B, and location C. And we have two bearings. So bearing this bearing D, and then we have bearing this bearing E. So in our case, each pulley carry an out of balance mass as indicated, determine the magnitude of out of balance forces at bearing D and E. When the shaft rotate at 1000 RPM. So we can solve this step by step. So the first thing is you are given this omega here. So omega which is given is 1000 RPM. So from here we can calculate omega square, which you can say that in radian per second. We will divide by 60 and multiply by 2 pi, and then we make it square. So this will be 10966 radian square per second square. So we calculate omega square because we want to calculate the actual forces here. So in the question, as you can see, you are given MA are A, MB are B, and MC are C here. So you are given these here. Okay, just one thing. I need to connect my mouse with this iPad, so then it will be easy to work with, and you will be able to see the pointer. Okay, so I think it should be better now. So in this case, as you can see that this is omega square. So we calculate omega here. So omega is because we want to calculate the forces in radian per second. So that's why we need omega square. So now we can calculate the first force. So in this case, it's better to like draw some table here. So if you draw this table, then what we can say that we can have these forces, and so we have the forces here. Uh, so the first one is your M1, and then or you can say MA RA omega square, and then MB RB omega square, and then MC RC omega square. You have these three forces, and then what you can do is that you can also then calculate the magnitude of the forces. So the first one, if you multiply MA RA omega square, what you get is 329. This is Newton. And the second one will be 438.6 Newton. And then the last one will be 219.3 Newton. And now you can see that you can also calculate the X and Y component of these forces. And because you can see that the first force is here, the second force is here, and the third force is here, you can calculate its X, Y, and Y component of these forces. So if you look at the R, the force A. So if you draw these forces here, so this will be our F1. This will be, or you can say FA, and this will be the FB, and then this will be the FC here. So again, you can see that FA is only having the Y component. The X component is 0. So it's having only the Y component, and the X component is 0 because it's vertical. So this is 0. And the Y component is again the 329. Okay, so similarly for the FB, because it's just making an angle of 60 with the vertical. So with the horizontal, it will make an angle of 30. So you can calculate its X and Y component. So the X component will be 379.9, and the Y component will be 219.3 here. Similarly, for the C, because it's now in the third quadrant, so for the FB, both X and Y are positive because it's in the first quadrant. Force C is in the third quadrant, so both its X and Y component will be negative. So if you calculate the X component, it will be 109.7, and the Y component will be minus 189.9 because you are given the angle. Just you need to do the cos theta and sine theta, so you can do this. So far it is okay. Is there any question here? Okay, so if you calculate this, then what we can do now is that because we want to the requirement here, as you already know, that the requirement is that we need to calculate this reaction forces. So you need to calculate reaction forces at D, and you need to calculate reaction force at C. So these are unknown. So how to calculate these reaction forces? You know that the way it works is that we take summation of all the moments. So you can take summation of moments from D, which should be equal to 0, or you can take summation of moments at E, which can be 0, or you can take summation of all the forces, which is again should be equal to 0. So this is what we mean by this dynamic balancing. So now, for example, if we want to calculate the reaction force at E, then we will take moments at D. So let's use the first condition here. So we will use the first condition. So if you're using the first condition, so now these are the forces, but we need to now calculate the moments. So first, as we said earlier, that first you need to calculate all these moments. So if you take the moments from D point, then as you can see, because the force at A is in the upward direction, as you can see here. So FA is positive in the upward direction, but because the distance is negative, or this why the MA will be in this direction here. So you can say that the MA should be this one, and the magnitude of this this will be, so this will be just FA times DA, and you can calculate this. So you can call it, for example, MA, and this will be 329, because the force is 329 here, and you need to multiply this with the distance, which is minus 0.2. The distance from D to A is 200, so you change this to meter, and this become 65.8 Newton meter. You calculate this moment here, but now because we are doing the analytical method, so we need to calculate both the X and Y component of this force. And if you look at this force here, so the force is in the negative Y direction. So you can say that the X component is obviously 0 because it's in the Y direction, and the Y component is going to be minus 65.8 Newton meter. So this is the X component, and this is the Y component. Okay, so we managed to calculate the X and Y component of the MA. Now we need to calculate MB here. So now if you take the moments from D, so we know that the distance here is positive, which is 400 from D to B. And we know the force, which is 0.04 kilogram meter, but then here we change this to Newton, so which was 438.6. So, okay, so now after this, we are going now to this which should be in this direction. So this is what you can call it F, B, and then dB. So this is our FB which is, you can call it moment B. So FB is 438.6, and dB is the distance between D and B, which is positive in this case. So you can calculate this MB, which will be 438.6 times 0.4. So this will be 175.5 Newton meter, because it's a moment, so it's a Newton meter. And as you can see, the angle, this angle is 60, so this means that this will make angle of 30 with the horizontal. So this will be its X component, and this will be its Y component. So you can now calculate the X component of this. So the X component will be equal to, so it will be 175.5 cos 30, which is going to be 152.0 Newton meter. And then the Y component is going to be 175.5 sine of 30, and this will be 87.7 Newton meter. And the important point to note here is that because both X component and Y components are positive here, because this is in the first quadrant, so that's why both X and Y are positive. So this is done now. Now we need to calculate for the FC here. So the FC here is in the third quadrant, which is somewhere here. So this is our FC. So FC is the moment will be FC and DC. And because it's making an angle of 210 here, so this means that if you calculate this angle here, so this will be 60 degree. And its X and Y component will be just this. So this will be the X component and this will be the Y component. And you can see that both components are negative in this case. So first let's calculate the MC here. So MC is the force is 219, which is 219.3. And then the distance here is the distance because we are taking moments from D. So from D to C. So this means that 1500 minus 200, so 1.3. And this will be equal to 285.1 Newton meter. So this is how you calculate the MC. And now we need to calculate its X and Y component. So if you calculate the X component of MC, that will be 285.1 cos 60. And obviously this will be negative. And the Y component will be minus 285.1 sine 60. So if you do the calculation, this should be minus 142.6 Newton meter. And this will be 246.9 Newton meter. So we managed to calculate the X and Y component of all these moments. So now you need to apply this this condition, which is summation of all the moments at D equals 0. So now you need to apply this to calculate the reaction at E, because we are taking the moments at D. So we need to calculate the reaction at E here. Now, because we don't know the direction and we don't know the magnitude of RE, which is both unknown. So we can assume that this is our RE. So you assume that it is very positive. So this means that this is our RE. So you assume that this is theta E. So in the first quadrant, and similarly, then the moments will be in the same direction. So because in the case of the moments, you are given this distance, which is 1200 from here, and then from here it will be 1200 minus 200, so which will be 1 meter here. Okay, so now if we calculate this moment of you can say ME, so this will be RE, and then the distance here is DE, which is obviously 1. And you can calculate its X component, which is RE DE cos theta E. And the Y component will be RE DE sine theta E. But obviously both RE and theta E are unknown, so we don't know those. And we are assuming that these are positive here. So after the calculation, if we get RE negative, so this means that the assumed direction was wrong. So it should be in the other way around. And similarly, if the y direction is wrong, then you get negative. So then it will be the other way around. Okay, so we calculate all these components. Now we can what we can do, we can now just apply this. So what I'm doing here are that I'm just using summation of all the moments at d equal to 0. So I'm using this equation now. So we will apply the same equation in both x and y direction. So first you will apply the same equation in x direction. So in x direction, if you see here, for this case here, so for the you can say for the RE, so you can say that you have the REX, which is obviously the RE cos theta. So REX, and then the angle, the distance was DE, which is obviously 1. And then because we have all the components now, so in this case, this is 0 here for the MA, so 0. And then again this X, so which is 152.0 plus. Okay, and then this one negative. So you will add all the X components here. So this is 142.6. And if you add all these three, it should give you 0. So this means that, and you know DE, which is the distance from D to E, which is 1. So this means that in this equation, the only unknown is REX. So you will be able to calculate REX here. You can say REX will be equal to, so minus 9.4. So you calculate REX, and let's use here the y components now. Add all the y components. So if you add all the y components, so this will be REY DE, and then plus. So you add this one here. So this is the first one. So minus 65.8. So this will be minus 65.8. Okay, and then the other one, which is this one, so 87.7, which is plus, so plus 87.7. And then the third one, which is negative, so minus 246.9. And this should be equal to 0. So from here, you will be able to calculate REY. So REY will be equal to, in this case, it is 225. Newton meter. Okay, so we managed to calculate REX and REY from here. So if you see here, our REY is positive. So REY is positive and REX is negative. So then you can easily draw this this case here. So for example, if this is your coordinate system, so this is our X and this is our Y. So you can see here that REX is negative. So this should be in this direction. And this is 9.4. And then the REY is very big as compared to this one, but it's positive. So this means that it should be in the positive y direction. Let me move it a little bit down. So in this case, you can say that it should be somewhere here. and this is 225. So I'm not drawing it according to the scale, but this is just how it should look like. And then the resultant one is this line here, from here to here. So this is your RE. So this one is REX. This one is REY. And then this one is your RE. And then this angle, which is your theta E. So from here, now you can calculate this RE from both its components. So REX square plus REY square under the root. So you do this, and then you get RE from here, which is 225.2 Newton. And you can calculate the angle, so which is going to be tangent inverse 225 divided by 9.4, which is 87.6. And so this is also correct, but if you want to find the angle, for example, with respect to the X, so then you can also do that. Okay, so this was our to calculate the RE. So is there any question in this case? So far, is there any question? So is it making sense? Like, can you understand like what I'm doing? Okay, great. Okay, so now the second part is that we need to calculate is that we managed to calculate RE. Now we need to calculate RD here. So for RD now you can because if you look at this figure here, so you have D and you have E, and both reactions were unknown. So that's why we have to take the moments from D or from E, because we have to get rid of the one of the force. And you can do this by just taking the moments. But now because we have the other one of the force or reaction, which is RE. So now the only unknown is just one force, which is reaction D. So now we can even use the this second case, which is summation of all the forces. So which will be easier to use because forces is easy to work with the forces rather than the moments. So let's in this case use this second case. So summation of all the forces. So summation of all the forces is equal to 0 here. So we will do this. Okay, so if we take summation of all the forces equal to 0, so because we already have the forces here, so we don't need to calculate anything else because we already have the, in this table, we have the X and Y components of all these three forces, which we just need to add, and then we will get the result. So how it should work, because now we need to calculate again this reaction at D, and which is unknown. So again, what we can do that we will assume that RD is in the first quadrant, and this will be the theta D. So this means that so if you assume this in the first quadrant, so this will be the RDX, and this will be the RDY. So in this case, you are assuming that both the X component and the Y component are positive. So, but this is our assumption. So you will do the calculation, and if you get RDX negative or RDY negative, so this means that our assumption was wrong, and that should be then the other way around. Okay, so now we have all the forces, so we can do the calculation. So the first force, we have is this r dx, for example, in x direction. So this will be r dx, which is obviously we are assuming this is positive, so this will be positive. And then you have the x component of the first force, which is 0 here. You can see in this case here, which is 0. So plus 0. And then you have the x component of the second force, which is positive. So 379.6. And then you have the third, the x component of the third force, which is the FC. And again, you can see that this is negative. So minus 109.7. Okay, but in addition to these four forces, we also have a force, which is we just calculate here, which is you can say that the REX and REY, so the reaction force at E, which is also a force and which is also in the system. So we have to add it here. And you already have its x component and y component, so you don't need to do anything else here. And as you can see, the x component of this RE was negative and the y component was positive. So if we are doing the x component, so you will just add this minus 9.4. And all these should be equal to 0 if we want the system to be in equilibrium. So this means that this r dx is the only unknown in this equation, which you can calculate. So r dx will be equal to minus 260.8 Newton. Okay, and you can see in the calculation that it is negative. So this means that our assumption was wrong. It should be the other way around. Now let's calculate the y component of all these forces. So again, we have now 5 forces. So one is RD, RDY. Okay, and now we have RD. And now if you look at the table here, so the y component, so the first force, the y component of the first force is 329, which is positive. So positive 329. And then positive 219.3, and then negative 189.6. And then you will also need to add this reaction, which is REY, so which is 225. And this should be equal to 0. So from this here, you can calculate RDY, which is the only unknown now. And if you do the calculation, this should be minus 583.4. And this is all the forces we are taking as Newton. So this should be in Newtons. And obviously, this was in Newton meter. You can see these are in Newton. So we managed to calculate RDX and RDY. So now you can draw the updated diagram for this force for the RD. So just draw its x and y component. So the x component is obviously in the negative direction, which is in this direction, which is around 260.8. And the y component is again in the negative direction, the negative y direction. So this is your x and this is your positive y. So these should be in the opposite direction. This should be 583.4. And then the resultant should be this one here. So this should be our RD, and this should be our theta D. So as you can see that similar to the previous case, now we need to calculate RD from its two components, so which is the x and y components, so which will be RDX square plus RDY square under the root. So it will give you your resultant force, which is something like a 639 Newton, and theta D, which you can calculate by using tangent inverse. So 583.4 and divided by 260.8. So this will be around 65.9 degree. And if you want to calculate this angle with respect to some other axis, so then you just need to add and delete that angle. But this 65 is just this angle here, which is with respect to the negative x-axis. So you manage to calculate both. You can see here we calculate the RE. So because it's vectors, we need to calculate uh, its magnitude, which is 225, and you need to calculate the direction, which is in this case was 87. And this was in the second quadrant because one x was positive and y was negative. And this is in the negative, both are negative. This is negative and this is negative. So it's in the third quadrant. And the angle you calculate is this angle here. So I think this is, these are the two unknown that we need to calculate in this case here. And we managed to calculate both unknown here. So is there any other question? Okay, yeah, you are right that these should be newtons. Yeah, you are absolutely right. These are because these are the reactions, and the distance here was 1. So if you divide by the distance, you should get uh, 9.4 Newton, and REY will become 225 Newtons because these are the reactions, these are not the forces. So that's why. But another thing is because DE is 1, so even you can call these like if you calculate the moments. So if you calculate REX DE, so which will be the same magnitude, but then it will be Newton meter. And similarly, this REY times D will be in Newton meters, but REX and REY should be in Newton because these are forces. So is it making sense now? So anything else? So again, in the class test, or you can either use the first method or the second method. So the first method that we did last week was about the graphical method, and you should get the same result. Okay, so maybe then we can take a break of 10 minutes, and we can then start at 12 past 12, and then we will do the second part. So in this case, this was just to calculate the reactions, but now here in the part B, they asking us to calculate the balancing forces at A and C. So we will try to do the same. We will try to do the second part in after the break. So see you in 10 minutes. Okay, so now we can do this second part. So in the second part, it is about that it's proposed to balance this system by adding masses to pulleys A and C. So briefly explain how to determine the required masses and their angular position relative to MA. So we will not briefly describe, but we will try to solve the system. So can everyone hear me okay? Yeah. And can everyone see my screen? Okay, so as you can see in this case, again, we are doing it analytically. So similar to the previous case, you need to calculate all the forces. So this is the MA now, so which is your FA, and this was your FB, and this was your FC. So you have these three forces here. And now you can calculate these forces. So similar to the previous case, we can maybe draw the table again. And then you have the forces here. You have the so MARA omega square. Similarly, MBRB omega square and MCRC omega square. So this is the same as the previous case, nothing new here. And you can calculate the magnitude of the forces. So the first one was 329. And the second one was 438.6. And the third one was 219.3 Newton. And then you can calculate at X and Y components. So this will be 0 and this will be 329 and 379.9 and then 219.3. And then this one will be 109.7 and this will be minus 189.9. So in this case, as you can see that we calculate all these X and Y component of all these three forces. So now in the previous case, you are asked to calculate the reactions at D and the reaction at E. But now the question is a bit different. So what you need to calculate, so the requirement here that we need to balance this system. So if the system is balanced, then there will be no reaction forces. But obviously the system is not balanced initially. So with these unbalanced masses, as you can see here, the system is not balanced. So you need to add the balance. You need to add some masses to the system to avoid the reaction forces, which you calculate in the previous case. So what it's saying that it's proposed to balance the system by adding masses to pulley A and C. So now this means that you need to add two more masses to A and C. So this means that you can call this, for example, MA, and maybe we can call it MARA, so which is unknown. And then obviously the theta A, which is in this case is known. So theta A, which will be the angle of this particular case will be unknown. The one that is given to you is, which is in this case is vertical, is just for this force A, which is due to this mass. But we now need to add another mass to this A here, which is this one here. And we also need to add another mass at C. So you can call it MCRC. So this is unknown. And again, you need to calculate theta C. So the one theta C, which is given here, this is 210, is for this mass, but now we need to add another mass to the same place. So you need to calculate that also. So these are the unknowns. So obviously, this means that one unknown is at A. So one unknown is at A here. So one force is at A and one force will be at C. So these two are unknowns which you need to calculate. So obviously, if the system is fully balanced, so this means that summation of all the moments should be zero and summation of all the forces should be zero. If you want the system to be fully balanced. So what we can do here is that first, maybe we let's start with this case here. So if you want to, for example, calculate the MCRC and theta C, so what we will do, we will take the moments from A. So we will say that summation of all the moments at A is equal to 0. And this will give us the MCRC and theta C. And then we can use either the forces or moments to calculate uh, the RA and MA and theta A. So let's do this part first. So summation of all the moments at A equals 0. So this means that you are taking now the moments at A. So now this is relatively easier than the previous case because all the forces are on the one side. So you don't need to be concerned about the negative and the positive sign. So all are positive. So all the distances are positive. So then there is no issue with the forces here. So if you, again, similar to the previous case, you will have to take the moments. So if you take the moment from A, then because we have the FA, so obviously it will be 0 because it's at this uh, A, and the force is A, so the distance is 0. So the MA will be 0 here. So you can say that the MA of this because this 329 into 0, so this will be 0. So you don't need to make you don't need to worry about this one. Now for the second one, which is this FB. So FB, you will need to multiply with the distance, which is this distance here. So you need to multiply with the 600. So then you can say that MB. So this will be the uh, the force, which is 438.6 times 0.6. So now because we are taking moments from A, so the distance should be from A, so which is 0.6 here. And this will give you the force, which is give you the moment, which is 263.2. And this will be Newton meter because this is moment. And now you can calculate its X and Y component similar to the previous case. So the X component will be 263.2 cos of. So if you see the force here, so the moments will be in the same direction. If you draw the moment, so it will be something like this. So this angle is 30. So you can calculate its X and Y component. So this will be cos 30. And the Y component will be 263.2 sine 30. So this is 227.9 Newton meter. And then this will be 131.6 Newton meter. And the thing is, because this is in the first quadrant, so both X and Y are positive here. Okay, so after this, now we can calculate the moment of force at C. So the original mass, which was the force, so 219.3, and you multiply this with the distance. So in this case, which is 1.5, and then this will give you the moment, which is obviously 329 now Newton meter. And if you draw this moment, it will be in the direction of the force, so which will be in this direction. And you can say that this will be an X and Y component, and the angle here is 60. So this means that you can calculate the X and Y component of this. So the X component will be 329.3 cos of 60, and this will be minus 164.5 Newton meter. And the Y will be 329.3 sine. Minus 284.9 Newton meter. So as you can see that both X and Y components are negative because it's in this direction. So this is our MC, and this was our MB. Okay, so you managed to calculate this X and Y component of B and C, which is given here. Okay, so in addition to this, if you are taking moment from A, so obviously now there will be no reactions at D and there will be no reaction at E. So then there's no need to worry about these forces. The only other force that you need to worry about is the force which is due to this additional mass, capital, you can call it capital MC, or and the distance will be RC. So because we need to balance the system by adding this additional mass, so obviously we have to include this in our calculation. So you can call this, for example, MC1, and then the other one. So, okay, and now because we don't know about the direction and magnitude of that mass that we will add, so what we will assume that in the first quadrant, something like this. So we will assume that this is our, you can call it force C or something. You can call it like this. And and the so this will be the force, and then the moment will be FCRC, FC, and the distance will be AC. And the angle here, you can call it theta C, which is obviously unknown, which you need to calculate. So here we are assuming that in the first quadrant. So again, we will do the calculation, and if the calculation is giving us the same, the X and Y is positive, so then these are correct. Otherwise, it should be the other way around. Okay, so this means that if you want to calculate the X component of this new force, so which will be FCAC cos theta, and the Y component will be FCAC sine theta. So we have all these forces here. So basically we have three forces because the first one is 0. We have MB and two C's. So MC1 and this is MC2. Okay, so now you just need to add all these together. So how can you do this? So now we are taking the moments at A. So this is summation of all the moments at A equals 0. So this means that you need to add all these components. So this means that the first one, the X here was 227.9, and this was positive. This X component for the force C was negative, so minus 164.5. And then you just need to add this unknown component. So you can say this is the, and we assuming that this is first, this is plus. So this will be FC. And okay, so we call this FCX, and because the x component and the distance is AC here and equals 0. So this FCX is basically FC cos theta. So if you do this, then the only unknown here, because we know AC, so AC is 1500 millimeter, which is 1.5. So the only unknown here is this FCX. You can calculate from here, and this will be so if you calculate this, it will be something. So minus 42.3, and this will be in newtons. So we managed to calculate this FCX, and now we can, so this was when you just add the X component, now you can add the Y component. So the Y component, again, here is 131.6, and then this is the Y component, which is 284.9. And then this is the Y component, which is, you can say is positive. We are assuming is it positive. And FCY into AC equals 0. And this will give you FCY, so which in this case should be 102.2, and which is positive. So our initial assumption was that both are positive, so the X and Y. But after calculation, you saw that FCX is negative and FCY is positive. So this means that this one assumption was wrong, but this one was correct. So now you can draw the updated diagram. So this one will be the updated diagram. So this is our X component, this is our Y component, and then this should be our 42.3 in the negative direction, and then 102 is in the positive direction. It should be going in the upward direction. So 102.2, and then this is your resultant. So you can call this, for example, FC, and you can calculate this angle also. You can calculate now FC, which is 1 FCX square plus FCY square under the root. So which is going to be 110 Newton, and theta C will be tangent inverse 102.2 divided by 42.3. So this will give you the angle, which is going to be 67.5 degrees. So this means that you managed to calculate this force that you can add at C to make the system balance. So you managed to calculate its direction and also its magnitude. So is there any question so far? Is any confusion or any question? So is everything okay? Yeah. Okay, then we can go to the. So if you see the question, you need to calculate two things. So one was that you need to calculate is MCRC and theta C. So we calculate that here. And now we need to calculate the first thing, which is MARA and theta A. And now the easy way now to do it is that you don't need to take moments. because initially there were two forces. So the forces method was not appropriate because there were two unknown forces. But now because we managed to calculate one force, so we will be able to calculate the other force by just using the force method now. So for the other one, now we just say that summation of all the forces equal to 0. So we will just use now this method here, summation of all the forces, and we will be able to calculate MARA and also the angle. So this means that you just now need to calculate the forces in both X and Y direction. So in X direction, as you can see, you have all these forces. So you have 0, then you have plus 379.9, and then you have minus 109.7. But in addition to these three forces, we also have this, the force which is due to this additional mass at C, and which is this force here. You will also need to add this force here, the X component of the force, which is minus 42.3. So minus 42.3. And now because we are calculating this another force at A, so because that is the unknown force, so you will assume that this force is again in the first quadrant. So you can say that it is F A1 because A2, because we already have one force at A due to this you can see like we already have this one force at A, but now this is additional force at A. So that's why we can call it FA2, for example. And this will have two components. So one will be positive, one will be negative. You can call this maybe FAX, and you will call this FAY. And you can see that both these are positive because so this is our assumption. We don't know about the actual forces, the actual component of the force A2. So this is our assumption that these are positive. So we will need to add this assumed force, which was FAX, the positive assumption, and this should be equal to 0 here. So because everything should be equal to 0. So from here, you will be able to calculate RAX, which is the only unknown in this equation. So everything is known, only FAX is unknown. So this will be minus 227.9 Newton. So you calculate this FAX. Okay, so now you can take similar forces in the Y direction. So these are in the Y direction forces. So 329 plus 219.3 minus 189.9. And then this force, which is plus 102.2. And then you will have to add this FAY. And or everything should be equal to 0. So FAY should be equal to the only unknown in this equation. So you can calculate that from here, which is minus 460.6 Newton. So you can calculate this from here. And now you can see that you calculate FAX and FAY. And initially our assumption was that this is positive and this is positive. But after the calculation, this is negative and this is negative. So this means that both assumption was wrong. So now you can draw the updated diagram. So this means that it should be the X component, so which is 227.9. And the Y is also negative, so it should be somewhere here. So 460.6. And then this is the resultant. So this is the resultant here. and this is our theta. So resultant theta A, and this is FA. So now you can calculate FA here. So FA will be F AX square, FAY square. And this will be 519, 513.9 Newton. And then you can calculate angle A, which will be tangent inverse 460.6 and divided by 227. So from here, you can calculate the angle, which is 63.7. Yeah, so this is how you can solve this this problem here. So finally, you can see that we managed to calculate this part here. So in the first part, you calculate the balancing mass that you need to add to the system, and you calculate both magnitude and direction. And then in the second part, you calculate the magnitude and direction of the force that you need to add it A. So if you add these two forces at A and C to the system, then the system will be fully balanced. And by fully balanced mean that there will be no reactions at the bearings. Now, if you try to calculate reaction of the bearings by using all these forces and all these new masses, so including now you have 5 masses in the system, so 2 at A, 2 at C, and 1 at B. So if you try to calculate the moment at D and the moment at E, or at any other point, it should be 0. So this is the main idea of this balancing, that the reaction of forces should be 0. So any question? Is it this making sense? Okay, just one thing more. So this is about this question. So I think we don't have anything else about this question. Okay, so maybe I will stop this. Okay, so if you, I will share this another screen. We still have some time, so let's do it here. So I also upload this So can everyone see my screen? Okay, so if you see here, so this is basically your lab, so which you will need to do, or maybe you have done it already. So here, what you need to do, you need to balance. You need to do some calculation to calculate the balancing masses. So as you can see that in this case, you have this machine here, and you are given these 4 masses. So for each block, so you have these 4 blocks. And if you see the way these blocks look like is that these blocks are different. So the hole, as you can see, the hole is different in the block. So this one is a small hole. This is a little bit bigger hole, and then this is bigger than this one, and then this is the biggest one. So this means that the other sections are the same, but it's only this additional things that you are adding here. So due to this, you get different MR values. So in this case, the MR is given, which is 0.038, 0.036, 0.0337, and this is 0.0286. So this means that this is given to you. So this is given to you the MR values of all these blocks. So these are the known for your case. So this means that if you see your assignment for this lab, so normally how it works is that you will be given for example, in there are like 2-3 cases in your lab book. So the case one is that you are given the theta 1 and x1 for mass 1, similarly theta 2 and x2 for mass 2. So this means that if we have these 2 bearings, so this is, for example, mass 1, mass 2, mass 3, and mass 4. So x1 is the distance of mass 1 from the bearing, x2 is this distance here, x3 is this distance here, x4 is this distance here. So this means that if you are given these distances, and if you add masses to these different locations, then the system should be fully balanced. So the questions that you are given is that you are given 2 masses. So for example, you will be given theta 1, which is equal to 0, which is the angle of the first mass. And the distance will be given, which is 20 in this case. And then you are also given the distance, which is 120 millimeter, and the angle, which is 100 degrees. So this means that you are given these first 2 masses. And the question is that you need to calculate the additional distances. So this means that x3 and x4 is unknown. And because you are given the MR, so you don't need to calculate MR here. You need to calculate theta 3 and theta 4. So this is basically the question, that if you add 2 masses, so x is, for example, if you look at this system here, so x is the distance from here. So the first mass, if you want to calculate the distance, so it's from here to here. And there will be a scale here, so you can measure the distance. So you can attach the mass and you can measure the distance from here. And similarly, there is a protector given here. So using this, you can measure the angle. So is the question making sense, that what you need to do? So you need to calculate x3 and x4, and you need to calculate theta 3 and theta 4. So these 4 are the unknown. So maybe if you do the calculation, so in this case, I'm showing this, that the x3 is bigger than x4, and x3 is bigger than x2, and x4 is bigger than x2 or x3. But it can be anything. So for example, in this case, if you do the calculation, so maybe x3 will be even smaller than x1. So it will depend on your calculation. So the full solution I uploaded to the Canvas. So you can this document is available there. So and again, as you can see, because you are given theta 1, so you can assume that this is 0. And you are given theta 2, so which is 100, so which will be somewhere here. And then because we don't know about theta 3 and we don't know about theta 4, so you can take these as in the first quadrant as we are doing in the other cases, because theta 3 and theta 4 is unknown, but you are given MR. So again, you can calculate F1, F2, F3, F4, which is just which is given to you, which is the MR values. And you can draw, for example, you can solve this example using graphical method, or you can use it using the analytical method. So for example, if I want to solve this problem graphically, so what I'm doing here is that because you can see F1 is given is 38, you draw just one line in the X direction, and the length here is 38. Then you can draw another line in this direction. And because you know the angle here, which is 100, so the force will be in 100 angle direction. And it is 36 here. Now we have these two known forces with everything. So we know the distances, we know the angles and everything. Now we need to calculate x3, x4, and theta 3, theta 4. So how we will do this? Because now we don't know x3, x4, we don't know the angle, so we cannot draw these lines. The only thing that we know is that these forces. So the only thing we know is that these forces, and this is our force polygon. So what you do here is that you open your compass and equal to this, for example, F3. So here it is 33.7. So you will open the compass, and from here to here, you will draw this arc. And the arc, or you can draw a circle of radius 33.7, which is this circle here. And then you will, using this as a center, you can draw another arc, which is this one here. And then this is 28.6. So both these arcs uh, will uh, will intersect each other at this point. And then you can draw one line from here to here and one line from here to here. And you can see from here that this will be your angle 3, and this will be your angle 4. So this means that from the force polygon, you will be able to calculate theta 3 and theta 4. And if you calculate theta 3 and theta 4, so then you can draw, for example, your diagram, something like this. So we initially assumed that both theta 3 and theta 4 is in the first quadrant, but now after the calculation, you can see that theta 3 is something like a 191 and theta 4 is 272. So then it will be something like this. This means that mass 1 is here, mass 2 is here, mass 3 is here, and mass 4 is here. Now the unknown are x3 and x4, which is we need to calculate because we need to place these masses at some horizontal distance. So you need to calculate x3 and x4. So now we will do this using the moments, because the moments can give us these distances. So, and now because we don't know about the x3 and x4, so you just assume that these are somewhere here. So both are on the right hand side of the M2 basically. So you assume that 3 is here and 4 is here. So what you do here in the calculation is that now we need to calculate this L3 and L4. So if we manage to calculate L3 and L4, then this is what we need to calculate. So what you can do, you can just take moments, for example, from 1. So if you take the moment from 1, then you can draw this this polygon here, and this will be our moment polygon. So what you do here, because as you can see here in this figure here, that this was because we are taking moments from 1, so the force will not produce any moment because we are taking moments from 1. Now we need to take another moment from for the mass M2, so which will be in this direction. So you can see, you can from this point at an angle of 100, you can draw this length, and you know the magnitude of this M2, which will be the force times 100. So 100 is this distance. So this will be M2. So you draw M2 here. Okay, so you draw M2. Now, because M3 will be the force times the distance, but we don't know the distance. Similarly, M3 will be F3 multiplied by the L4, but we don't know L4. But we know the angles here. We already calculated the angle. So we know that the force should be in this direction and the moment should be in this direction. So what you can do, you can take this point and you can just draw, you can draw a line here. You can draw this line here, which is at this angle with the horizontal. So 191.7. So you can see this angle, which is, you can see this angle is 191.7. So you just draw this line. So if you draw this line here, and then you can see you can draw another line for 4, which is making this angle here 272.49, which is this line here. So this means that, and this should be a closed polygon. So this means that this should goes here and then this should goes here. So if you calculate this, then this should give you everything. So now you calculate this distance here by using ruler, and you calculate this distance here by using ruler, and this is 0.471, and this is 3.6 something. So M3 is 0.471. Okay, now the thing that you need to understand is that M3 is in this direction. So this means that it's in this direction. But M3, as you can see in the figure, is in the opposite direction. So this means that M3, so if you calculate this L3, this is basically negative. The M3 is negative because it's opposite to the mass. So this means that the distance is negative here, and this why it should be negative, and this why L3 is negative. If you calculate L3 here, so if you see here, L3 is something like a minus 13 point something. So this means that L3 is from here to here. So because we assume that it was here, but it's basically here. And then you can calculate, because L4 is in the same direction is the moment in the moment. So then it's a positive. So this means that this should be 146.05. So I think this is a bit different than the previous example. But the idea is the same, that you have to draw the force and moment polygon. In this case, the difference is that because you are given all the forces and you are given all the forces, and you need to calculate these two distances. So the distances are not given. So that's why we starting with the force polygon. We cannot start with the moment polygon because the distances are not given. So if the distance is not given, you cannot calculate the moments, and we cannot draw the moment polygon. But we can draw the force polygon because there are just two unknowns, two angles, because all the forces are known, the magnitudes are known. Only the two directions are unknown, so which you can calculate from here. And then the two unknown distances we can calculate from the moment polygon. So this is basically your one of the lab. So you will have to do this calculation, I think, to submit as a lab report. So you can. There are also other two cases in the lab report, but normally you need to just do one case because there is a limited time. So I took this as a first case, and you can see I solved this problem first graphically, so using this, and then I also solved the same problem analytically, which is given is here. So it's the same procedure, but using analytically. So you can see I'm doing it analytically, and then I calculate the results, and which is exactly the same as the is the graphical method. And all this is available online. And just one thing more is that I also solved question 2 in your tutorial using the analytical method in one of the video. And I also solved the same question 2 graphically, and it's also available on Canvas. So if there is any other question, so feel free to ask. And I think this should, yeah, so it's recording, so everything you should also have is a, I will share the link of this recording. Any question? Yes, go on. Zod, do you have a question? Do you want to ask some question? Then unmute yourself if you want to ask.